Hi friends, let's learn about databases in a very applied way now. Again, databases is one such subject at undergraduate and graduate level which is extensively used in the real world. If I have to pick one subject apart from programming, right? So apart from basic programming skills, right? If there is one subject that I have used extensively during my own professional career, I would say it's databases. And I've seen hundreds of software engineers using databases on day-to-day basis. So if you want to pick one subject which has the most impact on your professional career, you should be good at databases in general, right? So what I'll do here is I'll give you an applied overview, right? So this is not a dive deep into each of the topics. That we'll do through the rest of this course, right? First, let's get a very high level overview from a very applied sense. We'll understand what all topics are there. Then we take each topic, spend a few hours on each topic, understanding the nitty-gritty details. This is an overview. So throughout this course, I'll make a fundamental assumption that you're a software engineer at an e-commerce company like Amazon or Walmart or Flipkart, right? So I'll try to take as many examples as, I'll try to give a wide spectrum of examples from the e-commerce industry. It could be Amazon, Walmart, or it could be Flipkart, right? So again, this way I can connect many of the concepts in databases to my own professional experiences, because I've worked at Amazon myself for about 5 years and I've seen tons and tons of databases being used left and right. So I'll try to give as many real world examples as possible so as to both motivate the concepts and so that you appreciate why a concept exists and why it is used in the real world, apart from just teaching you theory. So we'll cover all the aspects of theory, but we'll do it from a very, very practical and applied standpoint, as our course name suggests, right? And we can do a great job, especially for databases, okay? So I'll keep assuming that you're a software engineer at Amazon, Walmart, or Flipkart, and keep giving you examples from these companies so that you can connect the theory that you're learning to some real world software engineering itself, okay? So before we get started, let's assume we have a task. Let's assume we are a software engineer at Amazon or any other e-commerce company for that matter, and we have a task. Okay, let's write down the task. Okay, the task for us is to design a data store, right? We want to design a data store. Forget about databases, all of that stuff. Amazon as a company, if you think about it, has tons of data that it wants to store. Now we want to design some mechanism through which we can store all of this data. We'll see again. This is the foundational reasoning why databases came into existence in the first place. Again, even before databases became popular in the 80s and 90s, right? This is when databases became extremely popular. Even before this, people were storing data on computers, right? It just became much more the classical databases or the relational databases as they're often referred to. Again, databases themselves have seen huge evolution over the last 40 years, right? Right. So databases themselves have changed a lot. There have been a ton of companies, ton of great researchers who have contributed to this whole revolution. Okay. So let's assume our task is to store all of the data that is being generated at Amazon. Okay. That's our task. Now we'll try to learn the whole databases from this viewpoint. So, and we'll learn ton of theory also. Remember that theory is very, very important in general because theory lays the foundation work for us to understand the practical concepts, right? So we will learn about relations. If you recall, we have learned about relations and sets in discrete mathematics, right? We'll use some of these concepts here. We'll use data structures like, we all studied binary tree, right? If you recall, we all studied binary tree in data structures. We'll use variations of binary trees called as B+ trees. So this subject itself is connected to many other subjects in computer science. So theory is certainly very important and powerful, but so is the practical understanding of it. Okay, so I'll try to connect everything as we make progress through this course. Okay, so let's play this role, right? You're a software engineer at Amazon, like e-commerce company like Amazon, and we want to design a data store for whole of Amazon. Before we even go there, look at all the data that Amazon has. Amazon has ton of customer data, right? Like customer logins, customer passwords. Right? So these are customers who go to Amazon to purchase things, right? Customer addresses, right? Customer phone numbers, right? The devices from which customers log in, their mobile devices from which customers log in. There is a ton customers' credit cards and bank account details. There is a ton of details about a customer that Amazon has, if you think about it. So does it have ton of details about products also, if you think about it. For each product, there is a product name. There is a brand. There is a brand associated with this product. There is price associated with each of these products. Again, I'm talking about very broad categories here. There is a ton of data. There is literally massive amounts of data. To give you a sense, Amazon stores petabytes of data. Amazon literally generates petabytes of data. Again, for those of you who don't know, a petabyte is 1,000 terabytes. Okay, so petabyte is approximately 1,000 terabytes. Right? We all know what a terabyte is, right? So I hope, because we've seen terabyte sized hard disks nowadays. Okay, so products have ton of details and data that we have to store. Similarly, customers purchase products and customers return products. If you've ever used an e-commerce website like Amazon or Flipkart, you make purchases there. So if a user has purchased a product, we have to keep a track of this. Okay, at what price has he purchased? At what time? So at what price has this customer purchased? What time has he purchased? What is the shipping address that we have to ship this item to? Then there is a bunch of inventory data that also needs to be taken into account. What is inventory data? How many products do I have? For example, if I'm selling, let's say MacBooks. Okay, suppose there is a product called a MacBook. Okay, MacBook, let's say 13-inch, right? I want to know how many products are readily available in my warehouses. Again, Amazon stores a lot of their inventory in these huge buildings called warehouses. Okay, it wants to know how many MacBooks do I have in a given city. All this inventory related information also has to be stored. Similarly, a lot of shipping related information also has to be stored if you think about it. Okay, for example, when a customer purchases a product, I note down this information in his purchases, and I also have to ship this to the customer, right? So customer wants to track their packages while it's in shipment. Customers want to know when will they get their shipment. Who is the shipment provider, right? So all that information customers want to know. So I need to store all the information about shipments. I also need to store customers provide reviews for products. Customers, when they purchase a product, they say, I like this. They give ratings and reviews. Customers give ratings and reviews to products. All this information helps other customers choose the appropriate product. All this data has to be stored, right? Similarly, there will be ton of customer service related issues that customer also has to take care of. If a customer gets a faulty product, he'll raise an issue or he'll call, right? And Amazon has to take care of either refunding him or sending him a new product, or if it's available. So there are ton of things that Amazon has to do. So if you look at it, all this data, so Amazon literally stores petabytes of data. All this data, again, when I said that our task is to design the data store, the task is humongous. Okay, this is just a small subset of data that Amazon stores. Okay, this is a small subset of data. This is a tiny subset of the data that Amazon stores. Amazon stores much more information than just this. For example, let me give an example here, right? So Amazon also stores information on which user, let's call a user as UI, product as PJ. If as a user, look at this, as a user UI, if I visit the page corresponding to product PJ, okay, this is a product page, okay, I'm considering purchasing this product. So I go read the reviews here, I see some question answers being answered by people, I read the reviews, I see the price, all of that stuff. A customer visiting a product page and spending time here is also important data for Amazon, because Amazon uses this information to recommend appropriate products. Okay, so this is used by Amazon's recommendation system to recommend new products. So Amazon literally is a powerhouse in terms of the data that they store on regular basis, right? So now as a software engineer, it's a phenomenal task ahead of us. It's a massive, humongous task, but it's also a very exciting task. Okay, so let's see how to design all of them. But before we go and design everything, we have to understand the big picture. Okay, we have to see, to understand the big picture, there are multiple steps here. I go and talk to various teams. And understand the basics of data. For example, look at this. There might be one team which is responsible for storing all the products information. Okay, so whenever a new product is added to Amazon, there might be one team which is responsible for adding that information. Okay, they might give unique IDs. So they might give unique IDs for each product. Okay, actually Amazon has something called as ASINs, Amazon Standard Identification Numbers. These are like unique IDs given to every product on Amazon, right? So you go and talk to various teams. There could be one product team, there could be one customer team, right? A customer team is responsible for getting all the information related to a customer, like their shipping address, whether they're prime customers or not, all this information, right? So in understanding the big picture, I want to see, first of all, even imagining designing this whole data store is a massive task. So first what we will do here is, we'll talk to our team which is responsible for shipment. We'll talk to another team which is responsible for customer reviews. And we'll understand the big picture here. While understanding this big picture, I end up drawing a bunch of diagrams. Okay. So this big picture, for example, this big picture could say, okay, that every user has a unique user ID, right? Every user has a unique user ID. Every product has a unique product ID. Let's call it PRID or ASIN. Okay. And a user can at a given time, there might be some business logic. There might be some logic which says a user can purchase a product, can only purchase 4 items of a given product at any time, not more than this. Okay, this is a business logic which you will understand only when you talk to the purchasers team, right? Similarly, they might say for this product, they can return this product within 7 days, and it's a free return. So there are lots of details about every logical thing, about every user, every product, every purchase, every shipment, every review, every customer service request. There is a ton of data, right? You understand all of this data and you pictorially represent this, right? You pictorially represent all of the information that you learned by talking to all these teams, right? Such pictorial representation is called an entity relationship diagram. Again, don't worry if you don't know what an ER diagram is. Okay, we'll actually take the example of Amazon itself and I'll walk you through how to draw ER diagrams. But before you even start designing your data store or how to store, how to search, all of those tasks, first you have to understand what data is available and how data is related, how different pieces of data are related, how different pieces of data are related to each other, right? So how different pieces of data are related to each other, right? For example, I told you, right? For a given product, there might be a specific number of days under which we have to return. So all this is business logic and business relationships, okay, that you have to understand. Again, I will go into each of these topics in depth. But the very first thing that we often do is we understand how each of the pieces of data. What is a piece of data here? Like a product is a piece of data, right? Something about a customer is a piece of data. For example, for every customer, there is a unique login. That's an important realization. And you can say every password should have at least one alphanumeric character and at least should have one special character. That's also a business logic, right? So every customer should have a phone number which is a specific number of digits, right? So all this information, we want to get a big picture and understand how different pieces of data are related. And we represent it pictorially using a ER diagram. So in a nutshell, an ER diagram gives us the big picture. It gives us the big picture of everything that we want to store and how this data is interrelated. Okay, it gives us the big picture view. Again, we'll see a ton of ER diagrams and understand tons of relationships as we progress through the course. Okay, first is understanding the big picture. Once I understand the big picture, we think of something called as tabular structure. Again, if you think about it, right, forget about databases, everything. If you have seen old ways, okay, pre-computer, if you have seen pre-computer, some of you who are young may not know how pre-computer age worked. People actually stored a lot of information on books. Okay. So for example, imagine if I'm a shopkeeper. Okay. I would actually make a book which says, okay, what is the product? Okay. How many did I purchase? Okay. Number of items that I have in my shop now. Okay. On what date did I purchase? How many more should I order? So they would actually store this in a book. They would actually write this in a book. So this task in retail is called as bookkeeping. Okay. Again, if you have seen banks before the pre-computer age, even banks had this, where they would have these big books or catalogs, where they would actually write down how much money you have deposited. And they would actually, If you want to know how much money is there in your bank account, they would actually open the book, these big bulky books, and all the data was stored in tables. At the end of the day, all of this data was stored in tables, right? So if you look at this, let's say a product could be, let's say, Nike shoe, right? How many items do I have? I have 5 items. On what date did I purchase these items? How many more do I need to order from the supplier? All this data was stored in tables, right? Even in a pre-computer era. So when databases came into existence, people said, we know how to do bookkeeping using tables. Okay, this has been done for a few hundred years by human beings, very successfully. There are some standard strategies on bookkeeping, which many merchants have designed over generations, right? So databases community said, okay, tables is something that all of us understand. So we will store all of this data in a tabular form, right? So we have to now, once we have understood the big picture, we have to decide how many tables we'll store this data in. What should each table contain? These are important questions, right? So what should each table contain? What information should each table contain? And how many tables should I create? Number of tables I should create, right? Number of tables I should create. And while creating all this information, while doing all of this, very importantly, I want to minimize my storage space. While doing all of this, I want to minimize my hard disk storage space, right? This was one of the big challenges. If you think about it, in the 80s, when most databases were designed, there was very limited hard disks to store this information in, right? So people said, how do I minimize the hard disk space needed to store all of this information? It was very important. So there is a mathematical model behind how to store data into tables called the relational model. Okay, called the relational model. Again, this whole relational model, as in the name you have relation, right? This whole relational model is related to, or it's very deeply connected to, relations that we learned in set theory in discrete mathematics. Okay, if you don't know, don't worry. I'll repeat some of these concepts. I will quickly summarize some of these concepts. I'll quickly give you intuition behind what a mathematical relation is. So a lot of mathematical machinery that was designed on set theory and relations was used in databases, right? So we'll see how a table is a relation. So there is a mathematical model that mathematicians and computer scientists started building on how to design tables optimally, right? Very, very interesting concept. Okay, so this is the second aspect. Now at the end of the day, see here, if you think about it, I'm storing the data in tables, but physically I have to store it on the hard disk, physically. At the end of the day, everything has to be stored in files and folders. At the end of the day, on your disk, you have to store it in files and folders. Now, how do I store all this data in files and folders? How should the file structure design be? How should the files be designed? How should the files be designed? Very important question, right? Again, there are tons of files. If you remember simple file handling in C programming, right? If you recall, if you know C programming, you would have seen things like fprintf, fscanf, fseek, all these functions, right? They all help you handle files, right? Now at the end of the day, all of your data has to be stored in some files on your disk. Now how do I use all of this file handling stuff that I've learned optimally to store the data on disk? That's a very, very important aspect, right? Very, very interesting. And again, throughout this process, I want to minimize the amount of space that I want to store on my disk, because especially when databases were designed in the 1980s, hard disks were very expensive. But if you notice, from the 2010 onwards, hard disks have become extremely cheap, right? So there is a huge revolution within databases also, right? So the databases that we learn of mostly in this course are databases which have been popular in the 90s to 2000, this period. So from 2010 or from the late 2000s onwards, there is a new revolution called as non-relational databases, right? There is a whole area. So all of this, the relational model of databases was extremely popular from 80s to 2000s. But from 2010 onwards, since hard disks became very, very cheap, there is a whole area called as NoSQL databases or non-relational databases, which we'll touch upon briefly at the end of the course. Okay. So now, how do we store it? That's a very important question. And when I store it, very importantly, I want to search and retrieve information very fast, right? Imagine if I'm a customer who logs into Amazon. I want to look at all of my past orders. Okay, I want to look at all of my past orders, or I want to search for a new product that I want to buy. So this is about retrieving some information from my data store. This is about searching some data in my data store. This has to be super fast, right? This has to be super fast and super efficient, because people don't want to wait, right? Now, what data structures will we use here is an important question. If you recall, we have studied something called as a binary search tree. If you recall, we learned something called as binary search trees, which are extremely powerful, because if you recall, in data structures and algorithms, we said I can search in a binary search tree in order of log n time if the binary search tree is balanced. Okay, we learned some very interesting properties of binary search tree. So now in databases, we learn some nice extensions to binary search trees called B plus trees and B trees. B trees and B plus trees. Very, very powerful concepts. Beautiful concepts. Okay, these are simple extensions to binary search trees. This will help us search and retrieve information very, very fast throughout this whole process. Right? Now, another very important thing is something called as a multi-system access to your data. Let me give you an example, right? Suppose I have inventory data. Okay. Suppose I have inventory table in which I'm storing some data about how many items for any given product do I have. So for example, let's assume this is my table. Okay. This has some product ID. Okay. And some number of items available. Now, if you think logically, when a customer purchases this, the software which enables a customer to purchase, right? This purchasing system accesses this data. When a customer purchases this data, this number of items will reduce by 1, right? Similarly, there is also product acquisition, right? So this is customer purchasing it, right? There is also the supply team. Okay, there is also the supply team which keeps buying new items and keeps entering that information here. Okay, this team obtains, for example, imagine this is Nike shoe. Imagine that this is Nike shoe. So there are people at Amazon who are responsible for stocking. So this is called the stocking system. Okay, what this system does is it actually orders from Nike, and whenever Nike sends some shoes, they'll increase the amount here. So if you think about it logically, the purchasing system and the stocking system, both of them have to access this simultaneously. Okay, both of them have to access this data simultaneously. So there is a case where multiple systems or multiple programs might access your data simultaneously. So you have to ensure that there are no logical flaws you want to ensure that when somebody is purchasing it and when somebody is stocking it simultaneously, there are no major bugs that creep in. Okay, so there is this whole area called transaction and concurrency control that we will learn of, right? There is this whole thing called as transactions and concurrency control. The job of this system itself is to ensure that when multiple systems or multiple processes or multiple programs simultaneously access your data, there are no logical flaws in how these numbers get incremented or decremented. Again, there are lots of details in transactions and concurrency control that we'll look at. Equally importantly, if you think about it, there is one more very, very important piece called as a structured query language, SQL. Okay, this is probably the most widely used system within a database. Okay, so again, if there is a lot of data that is stored in your database, you want to modify this data. So the multiple things that you can do, right? You can add more data, you can delete some data, you can modify data, right? Or you can search or retrieve for data. All these things, to be able to do all of these things, if there is a simple language to do all of these things very elegantly, there is a very simple language. Of course, remember, we can do this in a modern programming language like C, C++, Java, etc. But imagine if there was a special purpose language, okay, to make all of these modifications very, very efficiently. Such a language is called SQL. And SQL itself is based on the relational model. So we learn some mathematics also when we learn about relational models, right? So all these pieces are put together in a very nice way. And again, we'll keep tracking this example. Okay. We are a software engineer at an e-commerce company like Amazon, and our task is to design a data store. These are all the tasks that we have to account for. Okay. And throughout the rest of this course, I'll break up this problem into smaller and smaller pieces. First, we'll start with some basics of getting the big picture. How do you draw an ER diagram? How do you share the ER diagram with others? How do you make sense of an ER diagram? Right? Then we'll see we'll learn some relational algebra and the relational, again, there is a whole area, mathematical area in databases called as relational algebra. Very simple concept. It may sound very fancy, but it's very, very commonsensical. We'll see how each table is designed. How should we have, how many number of tables we should have? How do we minimize the amount of hard disk space? How do we store all of this data in files very efficiently so that I can search and retrieve extremely fast? And what types of special purpose data structures can I invent to solve this problem? And how do I ensure that when multiple processes or multiple systems are parallelly accessing my data, there are no inconsistencies that seep in, right? And at the end of the day, we will learn of a very, very powerful and very, very, beautifully designed programming language. I can't call it a programming language, but a beautiful query language called a structured query language, which helps us perform all of these common tasks on a database very, very efficiently, right? Instead of worrying about writing code in C, C++, Java, we can start writing simple SQL queries which take care of everything we do. Again, we'll also understand why SQL was designed in the very first place. Okay, so we'll discuss everything about why SQL was designed in the very first place, and I'll try to give you very, very applied arguments on why something is the way it is. Okay, let's get going. I'm super excited to start on this journey of databases with all of you.